Mesa de Canelon is telling you a story. You just have to have the background to understand that story. Being able to understand the ages of those rocks and how those rocks were formed, and therefore the story of that hill. The water, groundwater, as an invisible resource, is hosted in that story. So the more I know that story and the more I understand it, and the more I can project it down under the ground, the better I can tell the story of the water. And why is the water there? Why does it have the qualities that it has? Is it recharging? Is it not recharging? How long do we have on this landscape if we're groundwater dependent? And then I came in to help give them a story. And then over time I took over that network, which we started with 50 wells in Union County. And then Wagon Mound said, we want that same information because we think we're in the same, we're running towards the same problems here. As wells go dry, as wells fail, as our surface water dries up, what are our options? And for a lot of folks, they don't necessarily want to have to sue their neighbor over something because, right, the only people who are going to win that are the lawyers. But how do we figure out what we have and what we don't have, and how can we move forward with that information? What we've learned over the decade out here, we still have a very long way to go. When I first started working in Union County, when you come south out of Clayton, there's a little creek there called Seneca Creek. Perico Creek. And the farmers I was with said, well, we're a little confused because everybody's always told us that we're over the Ogallala and there should be oceans of water under there. So why are the wells going dry? And why are we having to lower the wells and lower the pumps? And why is this happening? We don't understand this because everybody's always said that we should be fine, but we're not. And also, why can my neighbor farm, and they used to have 800 gallons a minute in their well, and my windmill barely makes a half a gallon? Like, that's not fair. How come? And I said, okay, well, the first thing I gotta do is I gotta go find rocks. I have to learn my story because I can't tell you what's happening until I know the story. So let's go walk Perico Creek and let's look and see what's in the creek. And based on the broader scale geologic maps we had for Union County at the time, they mapped all that country as Ogallala. Okay, so this is where people are thinking, well, the map says it's Ogallala. I should be getting 800 gallons a minute and I get a half a gallon a minute. You know, what the heck? So, you know, it was January, which is always a great time to be out walking creeks in Union County, but we did it. So we walked the whole length of Perico Creek. It's 9 miles from Springer Highway to Narragansett Highway. And we walked it, myself and these two farmers. And we got 100 yards down that creek, and you know, I'm walking along and I'm looking down at the ground, I'm looking at the rocks that are starting to show up out of the mud and the dirt and the grass and the cow poop, and I'm like, oh, Houston, we have a problem. That would be the Dakota sandstone in the bottom of that creek. That is not the Ogallala. So what this means is your different rock types have different hydraulic characteristics. The Ogallala, if we think about it, you can think about it as basically a bucket of gravel and sand. And so you can put a lot of water in that, and the water moves easily in that. And this is how we can get 800 gallons a minute. The Dakota sandstone, which makes up a lot of the rimrock country for the Canadian River, for the dry Cimarron, for this lower stretch of the Mora River, that gold sandstone that makes up the rimrock out here, if you go and actually look at it, like go stick your nose up against it the next time you see it, it makes up the wall here that y'all are sitting on. That sandstone, if you look at it, does that look like that can hold a whole lot of water?
No.
Okay, it's fine grained, it's closely packed, a lot of it is very well cemented, so the spaces where the water would be is bound up with cement. And so when we think about an aquifer, sort of there's the two main characteristics we always think about are porosity and permeability. Porosity is the pore space that you can put water in. If it doesn't have a lot of porosity, you can't fit a lot of water in it. If it has a lot of porosity, like a bucket of gravel, you can fit a lot of water in it. And then permeability is how connected are the pore spaces. So you can have all the porosity in the world, but if those pores are not connected to one another, the water cannot move through that material, okay? So when we think about sandstone, it's kind of in the middle. It can have good porosity, but fairly low permeability. So it can hold water, but it can't give it very well. Gravel is the perfect aquifer, okay? That's what our Ogallala is effectively behaving as. And then we have mudstones and shales that are at the far end of, they can actually hold a lot of water, but they can't give it because they're so fine-grained that the permeability is very poor. So, for example, up in Colfax County, where it's mostly black shale wells, they have to drill wells that are 300 to 800 feet deep just to have enough column of water in there so that they don't pull the water out faster than the shale can give it. And so your well infrastructure ends up being controlled as well by your geology. So when we're standing in Perico Creek and I'm looking at that sandstone, I'm not looking at gravel. So I know already this is a big part of the reason why Union County is having a lot of the water problems that they're having, is the geology is already not correct. And so if your story isn't right, then the way your wells are acting isn't gonna make sense. So over time in our stomping of creeks and running around in like the dry Cimarron and other places where we can actually see under the grass, which I love grasslands, they're awesome, but they cover my rocks. So it is kind of hard to see what the heck's going on when I've got like 50 square miles of grass and one little creek that's 6 feet deep, and I'm trying to figure out what the heck's going on under there. This is where oil and gas exploration actually comes in handy. The area around Union County was wildcatted in the 50s and 60s when they were trying to find the northern edge of the Permian Basin and the western edge of the Dallam Basin. And so we do have a fair amount of deep logs. And the way that the data is collected from oil and gas wells is they run a packet of instruments down the hole after they've drilled it that collects a huge amount of high resolution data. And if you understand the properties that those instruments are capturing, like if I just showed you a petroleum well log, it would look like just these incredibly weird squiggles running down this really long piece of paper. But if you know how to read those squiggles, you can figure out what the rock units are that well drilled through. And then you can create this underground map of where the different rock units are in space based on that data. Most oil well drillers will go all the way to the basement. They go all the way to the granite, which for the Permian Basin, that's 20,000 feet. So you can see some incredible features under the ground by using that old oil and gas data. So what I've drawn here, and I'm going to try to call it out for those of y'all in the back who maybe can't see all of it super well. This is as though I went about 20 miles from the Texas state line, so I'm looking at Texas, and I took a bulldozer and I cut 800 feet down into the ground and just cut a giant ditch so that I could look at, this is what all the rock units are doing under the ground for 800 feet down, from basically Colorado down to Quay County. So we're looking east into Texas, and when I used to teach 101, Geology 101 at UNM and at Highlands, we tend to simplify things for that introductory course, and we would always teach that sedimentary rocks are laid down in horizontal layers that are all the same thickness and all the same everything everywhere. And that is in fact absolutely not the case. So very rarely do you get to see that. There are a lot of things that can disrupt that perfect deposition. You can have old topography that is having to drape itself over. You can have later things like mountain building events or extension of Earth's crust that break and fold and fault those rocks and create unevenness in the subsurface. And so something else that I hear a lot out here is, you know, my granddad had that well drilled in the mid-1900s and made 50 gallons a minute. Now it's down to 2 or 3. And so I scooted over a half a mile and I got my witch and sticks out. And I think I'm good. And I drilled there and I got a dry hole. What gives, okay? All these complications we're seeing, the reason the wells out here don't all behave the same. The reason you can farm at Sedan and Seneca, but you can't farm anywhere else. This well does 30 gallons a minute, that well does half a gallon a minute. Okay, all of that is related to what's going on under the ground. Okay, so as geologists do, I'm going to walk you from the oldest rocks to the youngest rocks. So we always start at the bottom of the picture because we have to tell the story in age order. So we're going to start way back in the Triassic. 220 million years ago, dinosaurs are just getting started. Fun little creatures that they were. They're now birds. So every time a bird poops on your car, that is a dinosaur being very upset that they are no longer the top people on the planet, okay? This is our way of getting back at you. Think about it. Chickens, think about how far we've fallen. Okay? That was T-Rex. Okay? So, let's think about that. So what are we going to be? So when we start down in the red beds, and the red beds along the Sangre de Cristos are an entirely different family of red beds than these. They're much older. But usually coming this way, you'll hear your drillers say, I'm going to stop at the red beds. If I'm drilling and I hit red beds, I'm going to stop because there's not water in them. The red beds out here are mostly mud. And so when you do get into them, they're not going to give hardly any water at all, unless you luck into just a little pocket in there. The red beds under a lot of this country were actually folded. There's salt beds under them that have deformed over time, and as they move and dissolve and recrystallize and dissolve and recrystallize, they cause those red beds to end up basically like this hummocky terrain. So we have all these folded beds under there. And that means if you're just drilling blind, you don't necessarily know if you're going to hit the top of an upfold, or maybe you're going to have a bit more space in there before you hit them. Okay, so you got to try to figure out how are these big folds oriented under the ground. Triassic ends, dinosaurs have taken over, and we come into a time when this part of North America was very dry, and it was covered with big sand dune fields. And these draped this beautiful sandstone over that folded and eroded landscape. And this rock unit is called the Exeter Sandstone. If you go down to Mills Canyon, you go in the Dry Cimarron Canyon, that peach-colored, really pretty soft-shouldered sandstone that's down low along the river, that's the Exeter Sandstone. And it does have openings in it that could potentially be bat habitat. See, I can tie these things together. So your Exeter, because it blanketed this really uneven landscape, its thickness varies from not there to 80 feet thick. So if you're drilling blind, you want to kind of have a sense of where am I not going to hit any sandstone at all versus where might I hit a nice thick pocket that has good water in it. There's a gentleman just south of Clayton, west of Sedan. He went 800 feet on just a blind hole. And he managed to hit one of these pockets in the Exeter. And he's actually sitting pretty good with about an 80-gallon-a-minute well. There are caveats to that I'll talk about in just a minute. But you could scoot over a half a mile and drill and never hit it. So over the Exeter, we have a unit. I'm going to skip one. Oh, I'm sorry. Did you? Okay. I'm going to skip one unit briefly. We have a unit called the Morrison Formation. The Morrison is famous for its dinosaurs. Every big dinosaur quarry in Utah, Wyoming, Arizona, the big dinosaur quarries are all in the Morrison. This is big long-necked dinosaurs. There's all kinds of cool stuff in it. So if you run around the Dry Cimarron there, you will actually find chunks of dinosaur bone out there. Folks use it as doorstops, which as a paleontologist is. So the problem with the Morrison is it represents a very complex landscape of marshy floodplains and through-flowing creeks and rivers and little ponds. And so instead of just one nice sandstone, that even though it's got its problems with thickness, you know it's going to be the same sandstone everywhere. The problem with the Morrison is it's going to be mostly a mudstone, which isn't going to give you any water. But within it, it has nested these fossil channels, river channels, that are snaking around through that mudstone. If you can manage to punch one of those, you can get a 30-gallon-a-minute well. But do you know where they are? Not necessarily. So the Morrison, a lot of drillers, if they don't stop at the red beds, they'll stop at what they call the blue shale. And the blue shale is primarily what the Morrison Formation is made up of. So it's very much a hit or miss potential. In eastern Los Animas County in Colorado, most of the subsurface there is Morrison, and so of the wells drilled out there, probably 80% of them are dry holes because they're just punching blindly trying to find these little river channels. It could be in width about as wide as under this awning. They could be maybe twice that wide, but you're basically out there drilling in tens of square miles trying to hit something that's the width of like this driveway. Okay. The Morrison, at the end of the Morrison, which is late Jurassic in age, again, that landscape gets eroded. It gets cut down into. And then North America, this part of North America floods with a shallow inland seaway. And the Dakota sandstone, which we've already beat to death, that represents that beach. The beach of that shoreline as it's coming west and starting to flood everything. That drapes over that eroded landscape. And so again, we have this problem of the thickness variations, because it's like with the Exeter, that Dakota sandstone is blanketing this landscape that already has big canyons and big ridge lines cut in it. And so, for example, this is right south of Sedan. There's actually a big ridge line of Morrison Formation that sticks up high enough that when you walk Tramperis Creek, you're in the Morrison. And if you go a half a mile north to Sandraw, you're in the Dakota at exactly the same elevation, okay? So in a perfect tidy world, your rocks would all be stacked in age order. But here we have a younger rock inset against an older rock unit, okay? And then, as if that weren't enough, in Colfax County, we have 3,000 feet of black shale. That's representing that ocean covering this landscape for millions of years. As that retreats, all that shale gets eroded off. It's really soft. It's really easy to erode. That's why folks who live in black shale country have the worst time with their roads, is because that shale just goes. As that's all eroded away, which is why here, other than under the basalt caps, we have no black shale out here, because it's already been stripped all the way off and we're back down to the Dakota. On that eroded landscape now, we're going to put our Ogallala. And the fun thing about the Ogallala Formation, it is one of my favorite rock units. At the end, as that seaway is retreating, we have another continent slam into the side of North America. And that crumples the western coast and it pushes up the Rocky Mountains. And as those Rocky Mountains are uplifting, what happens? We start eroding. As soon as you lift something up, it starts getting torn down. And so as those mountains are starting to erode, all those giant alluvial fans that are building off this newly risen mountain range are going to start to fill in this landscape that's been eroded down to the Dakota. And so you end up with these valleys full of gravel, and then you go a half a mile and you're back to the Dakota or to the Morrison. And then over time, as the mountain front is eroding, as this landscape continues to erode, we basically snip those alluvial fans off from the mountain front and we start to erode them too. And so what we end up with is this surface that's beveled, but we have these pockets of Ogallala that are basically preserved and protected under these grasslands. And I'm not really going to get into the whole volcanic story because that just screws everything up. But basically, you pop a bunch of volcanoes up in the middle of everything and it's just going to screw everything up. Volcanic rock is generally not, other than where it's really fractured, is not super porous or permeable. So a lot of times you end up with these ridge capping basalts that are protecting the rocks underneath them, which is really cool because then I get to see. But there are other features where the magma will come up along fractures, or it will move along the plains within the sedimentary rocks, and it will cool and crystallize, and it's basically forming these impermeable barriers in the subsurface that are either lying like a sheet or they're vertical. And so a lot of our ranchers in southeast Colorado, especially up around Spanish Peaks, where there's bunches and bunches of these vertical walls of magma, have realized that groundwater tends to pool on the uphill side of them. And so they always drill their wells on the uphill side of these walls of lava, because that's where the groundwater pools. But if you drill on the other side, it's completely dry. So they add a whole nother layer of complication to what's going on underground. So if we think about that big story that I just told you, what that means is where you drill your well is going to be, what you can do with it is going to be completely influenced by what you drilled through. So I have 4 wells on here. We have our classic Dakota well, and the blue dotted line is the water table in each of these little aquifer situations. The Dakota sandstone is probably the primary aquifer in northeast New Mexico and southeast Colorado. We have almost 500 wells in our network, and I'd say of that, probably 3/4 of them are Dakota wells. Never make more than 5 to 10 gallons a minute maximum. They're slow to give water, but they're fairly long-lived because the Dakota is frequently 200 to 300 feet thick, And if your driller actually drilled far enough down in it, you could have 100 feet of standing water in that well. And if you're careful with it, you can eke along with that. Then we have our Ogallala buckets, our little bathtubs like Sedan and Seneca. And back in the day, those used to give 1,000, 1,500 gallons a minute. Now most of them are down to 100 gallons a minute or less. And part of that is simply when you put that many straws in a bucket of gravel, no matter how much rain and snow you get, you are never going to replace how much was taken out in a single day to water up corn or wheat or whatever. There is some connection where the Ogallala is inset down into the Dakota. Water does move back and forth between those two aquifers. But it doesn't mean that if you have a Dakota well near an Ogallala pocket that you're going to be able to get the amazing amount of water that you would get, simply because the Dakota, as we've pointed out, is too fine-grained to give that water to you. So even if it had it, it can't give it. So in the Sedan Paleo valleys, that's, if you look down on eastern New Mexico, if you think about this on Google Earth, you'll notice we have these little pockets of center pivots that go all along the border. And then you get into Texas, and you get into Oklahoma, and then it's center pivot heaven, right? So basically, if we think about this landscape from the Rocky Mountains to the plains is dipped from west to east. And if we filled in that bowl with the Ogallala, these little fingers that come into eastern New Mexico, those are those last little edges of those old river valleys that have been filled in with gravel. And so instead of having the nice big rest of the bucket like Texas and Oklahoma have, we're in the little fringes of the bathtub. Think about it as though it's a scalloped bathtub, and so your water line is going to be very uneven, okay? So this does raise the problem that if you're, for example, a farmer in Texas, and you're cheerfully being a good Texan, bigger and better Texas, and you're just going to pump, what's going to happen to the folks that are west of you in the fringe? You're going to pull the water table right out from under them, okay? And this is what's happening in western Sedan. We've had wells going dry for about a decade now, and I can watch each year as we lose wells, I can watch that edge of the bathtub retreating towards Texas, okay? Now, most of the time, because of differences in cement, differences in this paleotopography, I like to have my landowners think about their well, each well, as though it's in its own little bathtub. Even if it is technically all in one aquifer, I want people to think about it as though this is my little bathtub and I need to husband my little bathtub. Because my bathtub may not be connected to a bigger source of water. It may not be able to recharge. It may be recharging too slowly. And it may be that if I don't husband my bathtub, in 10 years I will have no water. And so because of the complications under the ground, it's hard for me to say, yeah, your neighbor is stealing your water. Okay, that doesn't mean go shoot them. Okay, we have a legal system for this. She's lawyers, not your neighbor. But because of these complications, this concept of my neighbor is stealing my water may not be true. But vice versa, it could be true. So until you have information to tell you how your well is behaving and how their well is behaving, how deep is it to water? Is the chemistry the same? Are you even drawing out of the same aquifer? You may not be, okay? So basically what my team tries to do is take that knowledge and go out and learn how your well works and try to figure out for each well that we work with, what aquifer is it in? How deep to water is it? What is the chemistry, okay? These rock units all have different signatures. So when we take general chemistry and trace metal samples from a well, we can figure out which of these rock units is that water coming from. And a lot of these wells, we're not yet like Colorado. We still screen the whole length, right? Because we want any water we can get. If we got little water coming in at 20 feet and a little water coming in at 100 feet and a little water down at 300 feet, we'll take it all. So we can see where there's mixed waters, where we have different aquifers that are contributing to what's being drawn out of the well. So we're trying to take each well and say, where is your water coming from? Which aquifers are you tapped into? And then every 6 months, and most of y'all have actually seen us cruising around out here doing this, we'll go to all these wells that we monitor and we'll check the depth to water. Every 6 months, we stick a steel tape in there, and we see down to the 100th of a foot that's the precision that we go for. And what we're trying to do is every 6 months see over years, how does that well behave? And if you listen to landowners out here, what's the most common story we hear? My wells are going dry. They're not pumping as much as they used to. I had to lower my pump. I had to re-drill the well. I had to recase it, okay? What we're seeing in most of these wells is a failing system. We're seeing aquifers that are at the end of their life. And so when we come out here to measure depth to water, of those 500 wells that we work with, probably 75–80% of them are declining consistently, no matter what time of year it is. And it doesn't matter if we get the best winter snowpack or the best summer moisture, those wells do not come up. Very few of them do we actually see a winter measurement where we have a high water. Well, let me back up a second. So we measure in the height of the summer. My team's out right now doing battle with wells in Union County, so wish them luck. Yeah, if I don't get a phone call here in a minute, it's gonna be a good day. So we had some wells yesterday that were extremely poorly behaved, and so everybody's already grumpy. And now they're gonna go deal with even more poorly behaved wells. So we measure in the heart of the summer, which is tricky because the wells are on. And so getting that quiet water table can be really difficult. But what we're trying to capture is in the summer, when we have the hardest use on all these water tables, what does that do to the water table in each area that we work? How much does it pull it down? And then in the winter, when there's less use in general on these wells, how do those wells respond? How much do they come back up when you're not pumping them 24 hours a day? Do they come all the way back up to where they were the winter before? Or do they only come up a little bit? And then over many years, what is the trend on those water levels? Do we see a decline? Do we see a very variable behavior? Do we sometimes see an uptick and then a downtick? And we're also always listening to our landowners. Have you changed your practices? What are you doing? Are you using that well anymore? Are you not using it? Because all of that has to tie into the story of how each of these little water tables is behaving. So the patterns we see out here, like I said, is the vast majority of the wells we work with. These are 3 different hydrographs. So depth to water from land surface, time. The vast majority are doing this. We're just straight down, okay? Some by a few inches. Some of my sedan wells, prior to about 2015, were dropping 10 feet a year. Okay, if you're dropping 10 to 15 feet a year and you've only got 200 feet of water in that hole, how long have you got?
Not many.
A whole lot less than you thought you did. 200 feet sounds like a heck of a lot of water until you're using it at 10 feet a year, and then it's not. And then we have a small group of wells that are up in the winter. They go down in the summer when they're used. They pop back up in the winter, and they go down in the summer, and they just kind of do this. These wells over here with a consistent decline, these are usually wells with a depth greater than 100 feet to water. And our wells that we work with range anywhere from half a foot to, our deepest well is over by La Cueva, and it's 482 feet to water. Our longest tape is 500 feet. I really hope that well never declines that much because we will not be able to measure it anymore. And that one takes 2 people to measure that well. It is our least favorite well. Yeah, and then we get these that do a nice seasonal cyclicity. These are our wells that are generally in the 1 foot to about 30 foot depth, and they're located next to drainages. So when that drainage flows, you're just popping that well right up.
At that depth, you're probably in gravel?
Or sand.
Or sand, right.
Just the alluvial
Permeable.
sand.
Yeah,
Mm-hmm.
okay.
Yep, so you have a direct connection to whatever that creek's doing. Yep.
That's what, yeah, we'll talk about
Yeah.
adding to that.
Yes, and these are the wells that we would target for how do we get water back into a underground storage system, your water table, that you can then start to use again. Yeah. And then we get the ones that are in that 30 to 150 foot range that they do kind of try to respond in the winter. They do try to come back up, but they never make it quite up to the level that they started at. And so overall, the general trend on those is still a decline. It may not be as precipitous as some of these, but still over time, you're losing ground on that well, okay? So when we think about recharge, because that's one of the things we want to try to influence out here, especially when we start getting into healthy soils. You know, how do we get water back down so that it's stored and it's not just ripping off the landscape and heading to Texas, right? So, problems with recharge. Okay, one of the other sampling strategies we have out here is we take samples for an isotope of hydrogen called tritium. H3 decays to helium. When solar rays hit the upper atmosphere, it creates tritium naturally. And the rule of thumb used to be there isn't much naturally occurring. So if I went and stood out here during a rainstorm with a sample bottle, I shouldn't have a whole lot of tritium in my sample bottle. But when we blew up the atomic bombs in the western United States in the 50s and 60s, we put a giant cloud of anthropogenic tritium into the atmosphere. Most of that has now decayed away, and so it's less prominent than it was. But the basic rule of thumb has been, if you don't have measurable tritium in that bottle of water that I send to the lab, modern water from the 1950s or younger, is not getting down into your aquifer. That doesn't mean it's not eventually getting there. It just might take hundreds to thousands of years for water to get down there. If you have some tritium in there, we used to think that meant you had mixed old water and new water, old and new being relative. And if you had lots of tritium, then it's recharging probably from the season before, or just a year or two before. What we're starting to realize is there's actually sort of a fourth category. And we learned this from a couple wells on Fort Union Ranch that are shallow. They were in this 0 to 30 group, and yet they had almost no tritium in them. And we thought, well, that doesn't make any sense at all because they're in that soft sand alluvium. But we had one well come back with like 0.02 tritium units. And to us, that's usually a marker of no recharge. Sampled that well again after the 2017 monsoon. Okay, that was the year that we had a bunch of big floods out here. We had a bunch of water gaps ripped out. One of our ranches in Harding County got 6.5 inches in 3 hours. So you know that water's got to go somewhere. And so we went back that winter. We waited 6 months. We went back and we resampled that well. And it came back with 3 tritium units. So the drought is also effectively suppressing that recharge, and it's suppressing the amount of tritium that we can see in those wells. And so now you should always do this. You should always take into account all the data you have for that well. But when we have this 0 to 30 foot depth to water, even if the tritium comes back negligible, does not mean that the well's not recharging. It just means there's such a heavy drought signature in there that we basically aren't seeing the recharge because it hasn't been there. So when we're thinking about this as a marker, and the other thing that we've just done is there's a PhD student working out here who has sample collectors distributed all over the 4 counties to collect precipitation to look at oxygen and hydrogen isotopes, and she's looking at the sort of the upper part of the hydrologic cycle out here. During the pandemic, she couldn't come out to collect her samples, and she takes them every month, and so the water was just stacking up in those collectors. So we went out and we emptied the collectors in August, and then we did it again in February. So we had these 6-month samples, and we sent it to the lab and ran them for tritium. And we didn't know what we were going to get back because all the literature said out here we should get maybe 1 to 2 tritium units, and we were thinking that's what we're going to get. Well, they came back with 8 to 12 tritium units. So there's still a fair amount of, and we think it's naturally occurring, tritium. So we still have an awesome marker out here to use. I mean, I was thinking, man, if we're at the end of that big slug of bomb tritium, I got to hustle and sample all these wells before it decays away. But we're good. So, but we are, even just with those 2 sets of samples, we are seeing some really interesting seasonal variations in the amount of tritium, depending on where you are. So that's another little question that we're going to start chasing down. So when we think recharge, our wells that are shallow in that nice alluvium right next to a drainage where they can get water to them, those ones are the ones that are going to pop back up. Those are the ones that are going to have lots of tritium in them. They're gonna have usually pretty decent water chemistry because the water doesn't just sit there and dissolve minerals and get nice and gross. But the problem is, do we have enough rain and snow nowadays to help those shallow aquifers recharge? So tritium, having tritium in your well water is good news because it means that well can accept recharge. But then you gotta get the recharge to put in the groundwater. For most of our deeper wells, it's all of this that creates the problem. If groundwater moves as fast as your fingernails grow, how long is it gonna take for you to get water 150 feet down? That doesn't take hundreds of years to thousands of years. If there's not some barrier in there of lack of permeability that prevents water from even getting down there, even if it could. So for each of our wells, we're dealing with all these different factors that are gonna play a part in how that well behaves and how it can respond if we get enough rain and snow. So we're about halfway through our summer monitoring season right now. We've done Motor Wagon Mound, Colfax, Harding, and we're halfway through Union. Of all of our shallow wells, we were a little surprised because, you know, we've heard that it's been raining since May and we had good rain in March. Like, we actually had an amazing year so far for out here. All of our shallow wells are still down. So it takes more than a month or two for that water to get down there. Plus, is all that water gonna make it down even 20 feet? Okay, what's happening to it? Evaporation and plants. The plants are super happy. They're stealing all my water, okay? But this is again though coming back to the soil health and the cycling of that. How do we start to restore that balance so that when we have a healthy, diverse plant community on the landscape, at what point do we tip that balance so that you're holding enough water that not only do the plants get what they need, but maybe a little extra can now start to work its way on down to those shallow water tables. And so we're a big fan of trying to figure out how to restore the landscape in ways where we can hold water long enough to help it start to make its way down. In the San Luis Valley, we did some experimental work with geophysical imaging, looking under the ground with electricity to see if we could see where there were pockets of gravel so that we could stage ponds and ditches over those pockets of gravel so that when there is water coming from the western mountains out through their incredible acequia system out there, how can we potentially stage water strategically on that landscape to help that aquifer recover? And so there's all these different tips and techniques that we're trying to bring to the table. And so a couple innovations we've seen. In the farming communities at Sedan, I left a little Easter egg in my comments. I said up until 2015, those wells were falling at the rate of 10 to 15 feet a year. What happened in 2015?
Faster.
They changed their practices.
They changed what?
They changed their practices, okay? Because 2012 drought didn't do us any favors. Corn market bubble burst because they were growing high-grade corn. Market burst. 2012 drought, Union County got no measurable precipitation for 12 months. It was worse than the Dust Bowl. So what happened there though was they also for the first time got actual legitimate data. They got numbers for their wells and they could do the math and they learned what a tritium isotope was and why that's bad news. And the next year they shifted their crop types to low water crops, even with that taking the financial hit of moving to milo and to winter wheat and to, you know, triticale and smaller crop sizes. They changed their practices to husband that resource as long as they can. Now those wells drop less than a foot a year. That is impressive to me. Ranching communities, we have a lot of people turn the wells off when the cattle are out of that pasture. Timers, all kinds of tricks to manage every single drop, storage and pipeline systems. Everything so that you're not just, as he said, just pumping indiscriminately. Okay, it's managing every drop for what you need versus what you want. So